I spray it with the white. Okay. All right. So we this is weird. It's not the same notes. Okay. Last time we met, we went over the first derivative test again, right? So at this point, we know how to find the absolute maximum, the absolute minimum, right? The absolute maximum and minimum, we use the candidates test, basically come up with our critical points and then just plug it into f of x, right? And then with the first derivative test, we can figure out where the function is increasing or decreasing. And then as a result, we can determine whether it's a maximum or minimum, relative maximum or minimum. The second derivative test helps us determine concavity. And I don't know why the AP exam people think it's such a huge importance to know what the inflection points are, but they do. They will ask you about inflection points. And I just like, it's like they just pick that one thing. I don't know. So we need to make sure we know that, okay? Excuse me. Okay, if we look at this first example, we can see what's happening with our tangent lines, right? Okay, get my thoughts together. So we can clearly see that this is concave up, this is concave down. One of the things that we want to practice doing is making or connecting the relationship between f prime, and f double prime, right? So when we look at the second derivative, that tells us the concavity of the original function. But it also tells me where I have increasing or decreasing of f prime. Okay. So if we look at, let's see here, concave up means that f prime is increasing, right? So if a function is concave up, then f double prime will be greater than 0. Right? If f double prime is greater than 0, then I know that f prime is increasing. Right? Because f double prime is the derivative of f prime. Does that make sense? So if I just look at f prime and f double prime, then I can determine where f double prime is increasing or decreasing, because really it's essentially the first derivative test when we're just looking at f prime and f double prime. So if f prime is increasing on the interval and f double prime is greater than 0, then f is concave up. And then the same reasoning, here we'd have f double prime less than 0, okay? So if f prime is increasing, then it's going to be concave up. If f prime is decreasing, it's going to be concave down, okay? Okay, here's your test for concavity. That's what we just said. Okay. All right, so let's look at this example number 1. We've got f of x, determine the open intervals on which the graph is concave up or down. State the point of inflection. All right, so we have to take the derivative. To determine if it's concave up or down, what do we have to do? Take the second derivative, right? So let's see, this is going to be x squared minus 1. Okay, so f double prime is going to be 2x. So when we were doing the first derivative, we would take the derivative and we'd set it equal to 0 and we'd find those critical points. Well, here we're going to set the second derivative equal to 0. This is called a point of inflection. Okay. I should say this is a potential point of inflection. Does anyone know what a point of inflection actually refers to?
Isn't it just like the turning?
Right. It's where, well, it's not the turning point. A point of inflection is where it changes concavity. So like this would be a point of inflection. Point of inflection is where it changes concavity. Okay. Okay. All right. So we're going to make a table. Yes.
Would maximum and minimum points be points of inflection there?
Maximum or minimum points, not necessarily. Not necessarily. Because, I mean, look at that example I just gave you, right? This is a point of inflection here. That's not a maximum or minimum point. Okay. Okay, so we're going to make a table just like we did before. My point of inflection, possible point of inflection is 0. Okay. And we're going to look at f double prime. So I'm going to say let x equal -1, and here we'll go let x equal +1. When x is -1, f double prime is negative, which means f is concave down. Right? When x is +1, we get a positive number in our f double prime, which means f is concave up. Okay. So since we do change concavity, right? Since we're changing concavity there. Oops, that's not working. Okay, stop trying to be cute. Then x equals 0 is a point of inflection because f changes concavity at that point. Okay. So point of inflection is where it changes concavity. Okay. It's asking where it's concave up or it's concave down. So f is concave down from -infinity to 0. Because f double prime is less than 0. And f is concave up from 0 to infinity because f double prime is greater than 0. Okay? Okay. Pretty straightforward, right? All right, let's look at some graphing. The concavity and direction of the function is related to the slope of the derivative. Okay. Let's go ahead and graph this function and then let's talk about it. Okay, so 1/3 x to the third. Let's just take a quick look at that on the graph. Let's see. 1/3. Oh, what happened? X to the third minus x. Okay, let's just take a quick look at that. Okay, so it looks like it's got a maximum at -1, 1 and a minimum at -1, -1. Okay, so okay, -1, 1, 1, -1. I think it went through the point zero zero. Yep, goes through the point zero zero. Okay. So we've got a curve that's going like this. Okay. Okay, so looking at this curve, let's see if we can identify some parts, right? So right here at this relative maximum, we're going to have a horizontal tangent, which means what? What do we know if we have a horizontal tangent there?
It's like a relative. It's at least a relative.
It's at least a relative maximum, and we can see that from this curve, right? And what does that mean about f prime?
It equals 0.
F prime of x is equal to 0 there. Okay? Okay, what about this point down here where I have a relative minimum? What do we know about f prime? It's also equal to 0 there. Okay? Okay, what else do we know about this function, right? If we look at this, right, from here in that green section, what does that tell me about f prime of x? Right? Well, f is increasing, so f prime of x must be positive. Yeah, so f prime of x is positive. Okay. If we look here between those 2 points, what do we know about f prime of x? Okay. Why? Because the function f of x is decreasing there. Okay. And then if I look over here, what do we know about f prime of x? Yes, because it's increasing. Okay. So normally what we're going to do is we're going to have the f prime of x information, and then we're going to be asked to sketch f of x. Right now we're making those connections so that we can do that. Okay. Do I know anything about f double prime? Can you tell me anything about f double prime? What's the second derivative test tell us? Yeah. Right, tells me the point of inflection and the concavity. So I've got a curve here that's concave down until this point right here, and then it's concave up. So what's that point? That's a point of inflection, all right? So now if I look at this area from negative infinity to 0, what do we know about f double prime? F double prime is negative because it's concave down, yes. And then I also know about f of x. F of x is what? Decreasing, because f prime of x is decreasing because f double prime is less than 0. Okay, and then over here we have concave up, which means f double prime is greater than 0, which means f prime is going to be increasing. So here we know f prime is increasing. Oh my word. See, I should be in bed crying for no reason. F double prime is decreasing, and then here f prime is increasing. Okay. Okay. Definition of points of inflection. F is continuous on the open interval. Let C be a point of inflection. If the graph of F has a tangent line at this point, then this is a point of inflection line. of the graph of f if the concavity changes from upward to downward or downward to upward. Okay, complicated way of saying a point of inflection is where the concavity changes. It's also a point of inflection if f double prime is undefined or zero, but we already know about the zero part, right? So when we're looking here, bless you, this is going to be a point of inflection. Okay.
Critical point, not like with the second.
Yes, exactly. And this is a point of inflection, and this is a point of inflection. Okay. So we do have to consider where it's undefined. Okay. Okay, we're not going to spend time on this. We're going to move on. Because we could beat this to death for a week and a half, and we don't have that kind of time. Okay, let's go down to page 21. Okay. If C is a critical number of f of x, then f prime of C equals 0, or f prime of C does not exist. This makes x equals a possible maximum minimum value. Okay, so if f double prime is positive, what does that mean about f of x? If f double prime is positive, that means it's concave up. And what does it mean about f prime of x? It's increasing, yes. Okay. So take a minute to fill in the rest of that. Okay, if it's negative, we have concave down, and f prime of x is decreasing. The neither ones, this is where they get weird, okay? Neither means, this basically, what does that mean if it's neither? It's going to be vertical, right? Or it's going to be zero, rather. It's going to be zero. So if it's a zero, right? So if it's positive, it's above the x-axis. If it's negative, it's below the x-axis, right? So this just simply means this is a possible point of inflection, which means we have a possible relative min or max. Okay. So that's kind of a weird one. All right, let's see. Let's go down. Let's see. I think we're good there. Okay, let's go all the way down to page 24. Okay. Here's a summary. Okay, which is pretty much what we just talked about, right? F double prime is greater than 0. So if f double prime is positive, then f prime and f prime is positive. Then that means it's concave up and increasing. This is referring, that means f of x, right? If f double prime is positive and f prime is positive, then we know it's concave up and increasing. If f double prime is positive, but f prime is negative, then we know it's concave up and decreasing. If we have positive double prime, but it equals to 0, then we have concave up and we have a relative minimum. Okay, so this is your summary, all right? So here we have where f double prime is less than 0. We're either increasing in concave down, decreasing in concave down, okay, or a relative maximum and concave down. What would these look like graphically? We're talking f of x, right? So this is going to be increasing and concave up. So it's going to be like, oops, that's not even true. Increasing and concave up, it has to be going like this the whole time, right? Decreasing and concave up would be going like this. Relative minimum and concave up, well, that just means that it's going like that, but it's not going to continue going down. So that means it's not going like that. It's not going to continue going like that because I know it's a relative minimum. Okay. So basically that means that it's going to continue going something like that. Okay. Okay, whoops, what happened here? Okay, and then let's see, increasing and concave down, that's going to look like this. Decreasing and concave down will look like this. And then the same thing, a relative maximum and concave down simply means that this does not continue going up, right? Increase, okay, so if f double prime is 0, so that means f is increasing and that's a point of inflection. So it's doing something like this. So it's going to continue to be increasing, but it changes concavity. Okay, decreasing and a point of inflection. So that's going to be something like this, right? There's your point of inflection. The function is smooth and level and a possible point of inflection. Smooth and level. So f double prime is 0. F prime is 0. So that means, so if we look at the derivative function, right, that means it has a tangent, right? So the derivative function has a tangent that's equal to 0. But then f prime is also equal to 0. So this looks to me like it's going to be a straight line, doesn't it?
On 0, right? Like the x-axis.
I don't think it has to be on 0. But I don't know what the possible point of inflection is referring to. Maybe we'll see some examples of that, okay? Okay, let me see here. All right, let's look at this example above here. The table has selected values of g, g prime, and g double prime. The function is twice differentiable. That's important, right? So that we can do the second derivative test. And continuous from -4 to 5. Explain why there must be a value on -4, 5 such that g of c equals 7. Okay. Yes. Okay. So let's see. So we're going to say, okay, g of -4, that equals 0. G of 5 is equal to 8, right? 7 is between 0 and 8. G is continuous. Because it's differentiable, right? Differentiable implies continuity. On -4 to 5. Okay. Which theorem am I going to use to state? Yes. Intermediate value theorem. Yes. Therefore, by the intermediate value theorem, okay, let's get our wording right. There exists an x equal to c, right, on -4, 5. So I'm basically looking at this, right, as I'm writing this, on -4, 5, such that g of c equals 7. So these are what makes these hard is that you look at it and intuitively you're like, well, yeah, there's gotta be a value of 7 in there. You know it. You look at it, you reason it through, you're like, sure. The hard part's expressing it the right way, because it's like we know it, but how do we make sure that we can express it in a way that mathematically makes sense? So all the things that have to happen, right? We know it because it has to be continuous. If it's not continuous, then that's not the case, right? Because if this was not continuous, I could have something like, here's 5 and here's -4, right? G of 5 is 8. I mean, I could have something like this. G of -4 is 0, right? I could have something like that. There is no place in between where G of x equals 7, right? So that's where you really have to take the time to think through, why do I know that, okay? Okay, explain why there must be an x equal d such that g prime of d equals 8/9. Okay. Any thoughts on that? We're talking about a derivative now.
Did you do like the intermediate value theorem, but with the derivatives of -4? Like if you do f prime of 4 and f prime.
Let me, I wish I hadn't removed these. I'm sorry that I removed this. Let's look back at our various theorems that we're talking about. Things you should know. Here we go. Daggone it. Okay, I don't have it in front of me. But okay, so if we look at our theorems, which theorems did we have? We have an intermediate value theorem. What is it? We have a mean value. What else do we have? Rolle's theorem, and then the extreme value theorem. We know the intermediate value theorem, we just used it. It's talking about a value between the two y values existing. What's the mean value theorem say in general? That there's going to be a place where the average rate of change is equal to the instantaneous rate of change. That's the mean value theorem. Rolle's theorem says that if I have two y values that are the same, that there must be some place where there's a maximum or a minimum, right? And then the extreme value theorem guarantees me that I have an absolute maximum and an absolute minimum. Which one will we use for this one? This is talking about g prime, which is what? What's that called? That's a derivative, which means instantaneous rate of change. The derivative is the instantaneous rate of change. So this is saying, explain how I know that someplace on the interval between -4 and 5, there's going to be an instantaneous rate of change of 8/9. That's my mean value theorem. So in order to show this, what do I have to do with my mean value theorem? The instantaneous rate of change is going to be equal to what? The average rate of change. So we need to find the average rate of change. So I'm going to say G prime of D, right? The instantaneous rate of change is going to be equal to the average rate of change. So we're going to do G of 5 minus G of -4 over 5 minus -4. Okay. Well, let's see. This is 8/9. G of 5, that's 8. G of -4, that's 0/9. So we get 8/9 equals 8/9. So the instantaneous rate of change is equal to the average rate of change. So we have to state something about the theorem now, right? So G of X is continuous on -4, 5, and differentiable on -4, 5. I wish I had my theorems up here. I don't know why they're not there. Therefore, by the mean value theorem, okay, now I'm going to go back up and I'm going to look at the actual question right here. Okay. Uh-oh, where did it go? There it is. Therefore, by the mean value theorem, there must be a value X equals D on -4, 5 such that G prime of D equals 8/9. Okay. Recognizing which theorem, that's the hard part. Recognizing which theorem. Okay, so up here, this was a little bit easier because the 7 falls between the 0 and 8. Yep.
Why can't you use the IVT on the segment?
Because the IVT does not talk about the derivative at all. The IVT is simply saying if it's a continuous function, then that value has to fall between the two other y values. Yeah, good question. The intermediate value theorem does not refer to the derivative of all. Right. Let me pull up those theorems again. I've got to load them up again. A second here, because it helps to actually look at them. Here, I don't know why I can't. It won't let me download. Won't let me zoom either. I'm sorry. Okay. An intermediate value theorem, if the function is continuous and y is a number between f of a and f of b, there exists at least one x equals c on the open interval such that. There's nothing to do with the derivative here. Okay, this is just continuous functions, all right?
If the function you're giving is continuous, does that mean that f prime of x will be continuous? Like, will your derivative be continuous if the original function is continuous?
I want to say yes, and I'm hesitating because I'm trying to think of an exception. If f of x is continuous, is it possible that f prime of x would not be continuous? No, because differentiable implies. Okay, so yes, because it has to be twice differentiable in order for the derivative to be continuous. Because differentiability implies continuity. So If it's twice differentiable, then we know that the first derivative is continuous. Okay, the mean value theorem specifies that it's continuous and differentiable. Okay, the mean value theorem, your derivative is equal to your average rate of change. Rolle's theorem is continuous and differentiable. Okay, the extreme value theorem simply says that it is continuous. Let's see, if the function is continuous, then the function is guaranteed to have an absolute maximum or an absolute minimum on that interval. Okay, so the mean value theorem and Rolle's theorem have to be differentiable. Okay, so we go back to this one, right? This is the mean value theorem. It's talking about the derivative. Okay, and when we state it, we need to specify by the mean value theorem that it's continuous and differentiable. Remember, continuity on the closed interval, differentiable on the open interval. Okay, it takes time. It takes practice. As we do AP exam practice, you'll start to get the hang of this. Okay. Does g of x have a local maximum, a local minimum, or neither? And why do you say that?
Because that's the one that does like the maximum and the minimums, and then they give you at x is 3.
Okay, so the extreme value theorem specifies that it must have an absolute minimum and an absolute maximum. The extreme value theorem does not say anything about a local. Okay, well, see, that's what we have to be so careful, right? We get hung up on the theorems. What does it mean if it has a local minimum or a local maximum? What do we know? The derivative. So let's look at the derivative, right? Where is g of x, or is it equal to 0 anywhere? G prime of x is equal to 0 at 3, right? So g prime of 3 is equal to 0. Does everyone see that? Okay, if g prime of 3 is equal to 0, then x equals 3 is a critical point. Okay. If it's a critical point, there's a couple different directions we can go with this one. If that's a critical point, I could look to see if it's increasing or decreasing surrounding it, but I don't really know anything about increasing or decreasing. So let's go back and let's look at the table that we saw. Let's see, what was my question again? Is it a local maximum or a local minimum? Where did we have that table that told us? I thought we had one that told us that. Do we not? Oh, okay. I can look at increasing or decreasing from the f double prime. Okay. So let's look at this, right? If f double prime, or if g double prime is greater than 0, okay, everybody paying attention? This is taking some thinking and it's easy to drift, right? If g, okay, Caitlin, don't answer. If g double prime is greater than 0, what does that tell me? Okay, right? If g double prime is greater than 0, what's increasing? G prime is increasing, okay? If g double prime is less than 0, what's that tell me about g prime? It's decreasing. Okay, so if g prime is increasing and then g prime is decreasing, I can find a relative minimum or maximum for g prime. Okay, where can I go with that? What did our notes say? Because we can connect the double prime to the original function, right? Are you guys going back in your notes with me? What can we do? Okay, take 5 minutes to talk about it together because you're all just waiting for me to tell you. Turn to each other and talk about it. Turn to each other and talk about it. Any thoughts on this? Who's got an idea? Logan.
It's confusing because it looks like when you look at the G prime that like goes to the minimum, like it comes down and it goes up, it's negative, positive. But then when you look at the double derivative, it's a negative number, which would mean that it'll have to be concave down to here. It goes like that. But the other one was saying because like that's not really understand how we're booked.
Okay. So the fact that G prime is equal to 0 at that point, and G prime is changing from increasing to decreasing at that point, right? And then if we look at G double prime at this point, what's G double prime? -2. So that equals -2, which is less than 0. So that means G double prime is concave down here, right? So it's concave down, which means by the second derivative test, which I just had it open on my page and I just moved it. Okay, right here, using the second derivative to find extrema of a function. The second derivative is the first derivative of f prime. So the same relationships exist between f prime and f. Stay there for a minute. The same relationship exists, okay? So because, we're going to say because of that, so guys, stay there and finish your notes. By the second derivative test, you guys can go.
Attention teachers and students, can I please have Sarah Bell Martin to guidance?
By the second derivative test, g of x has a relative, is it a minimum or maximum? Maximum at x equals 3. Okay.